All right. So if you take one thing away from this talk, it is that the process of forming a star is messy. Now, after coming right after Benny, you guys have already gained some appreciation for just how crazy the process of star formation is. But I want to talk about some of the additional complications and why we then need things like artificial intelligence to help us understand the process. All right, so what do I mean by messy? So a galaxy like this one is forming stars throughout its whole extent. And the process begins not at the cloud scale per se, but actually within the galaxy itself. And those local conditions go on to tell you about the initial conditions of those gas clouds. So if you're part of a smaller gas cloud, you might form a wimpy little cluster. If you're part of a really massive gas cloud, like Benny talked about, you'd end up being part of a superstar cluster. Now, within these clouds, it doesn't form just one or two stars, but the typical one forms thousands of stars. And so the precursor of something like our sun actually comes from a very creatively named object in these clouds called a dense core. And this is a pre-stellar core, which would have formed a solar system like our own. Now, its conditions are inherited from the larger molecular cloud, and within it, the whole process of accreting mass onto the stars regulated by an accretion disk. So the evolution of that disk, and then ultimately even whether it goes on to form planets, depends upon the larger properties of the core that's embedded in. Now, this suggests that information is going from large scales all the way down to small scales. But actually it's a bit more complicated because there are a number of stellar processes that start on the scale of stars and go all the way up to the galaxy scale. So for example, not all the mass that's in that core winds up on a star. There's energetic outflows that actually sweep up and eject a huge amount of that material, so it never makes its way onto the star. So in addition, if you have a massive star, these heat and ionize the gas around them, and they sweep up these large bubbles, right? This is a really beautiful bubble created by probably an 8 solar mass star or so. And finally, if you have an even more massive star, then it will end its life in a violent supernova explosion, which goes ahead and returns all of that natal gas cloud back into the surrounding interstellar medium, and it completes the entire cycle of life to start all over again. All right, so in this scenario, we don't just have radiation and gravity, we have a lot of stuff going on here. So in my theorist perspective of this, you start with a gas cloud, then a whole bunch of complicated and nonlinear things happen, and then finally at the end, you get out a star. All right, so for my area of research, which does not involve superstar clusters, we can study the process of forming stars closer to home within our own galaxy and within our own galactic neighborhood. So here's a beautiful image taken by the Spitzer Space Telescope. Now this is actually only a small part of our galactic plane. It's only a small piece of our Milky Way. And you can see just what an incredible data set this is, how complex it is, how much is going on. So what it's showing you is the warm dust, where hot dust is in red, warm is in green, and these are actually these dense precursor clouds that are forming or will go on to form star clusters. Now, if we want to understand what's going on within the galaxy and its larger life cycle, we need to identify the locations where star formation is taking place and how those stars impact their environment. So just by eye, you can pick out a lot of little bubbles, right? So each of these is produced by a massive star driving a wind or ionizing its environment. Now, I picked these out by eye, but given the huge amount of data, that's not very efficient. And astronomers like myself like to spend more of our time doing numerical simulations and less time picking out features visually in large data sets. So one way around this is to harness the power of citizen scientists, for example, like yourselves. So you can put data like this online and allow people to log on and identify some of these interesting features for us, which then we can go and analyze and understand how these stars impact the local environment. So for example, if you go to this website, it will teach you how to identify these bubbles. And so you might see something like this. That's clearly bubble-like, right? So you would say, yes, it's a bubble. And then you would draw a circle around it to show exactly how big it is, which actually gives us information about the mass of the star and the energetics of how it's interacting with its environment. Or you might see this. That's pretty bubble-like. So you would say, yes, it's a bubble. Then you would draw a circle around it. But you might also see something like that, where it might be much less clear whether that's a bubble or not, or whether that's just some nebulosity or complex structure that's not related to a young star. So for my simulations, for my research, what I do is I replace this, right, like Benny, with this, right? So supercomputers to the rescue again to help us understand this data. So these simulations have a key advantage, which is they give us complete information, right? You know exactly what you put into the simulation, and you know complete information about the results that are coming out. So in these simulations, I'm studying the formation of more massive stars and looking at the impact of stellar winds and how they sweep up material in their environment. So here, this red is both hot and high velocity gas of a few hundred kilometers per second. Blue is intermediate temperature gas and tens of kilometers per second. And then the gray is the background cloud. So it probably has not escaped you that this image looks very little like that Spitzer Space Telescope image that we saw earlier. So we have to fix that. And we do this by carrying out synthetic observations, right? So we start with a simulation. Then we actually compute the photons that would be emitted if this were a real gas cloud in the Milky Way. And then we observe it as if it were a real object at some distance from us, right? And at the end, you get out images like these. So these are great because now this is a training set. You can fold this back into the Milky Way project to help train citizen scientists. Or you can try a different approach, which is artificial intelligence. So this is a little bit scary, right? So maybe it helps to, instead of the Terminator, to think about it this way, right? Much friendlier. All right, and so this has one advantage over citizen scientists, which is it's repeatable. So when you train the algorithm and give it a data set, it's going to return the same thing to you every single time, right? So this first approach to identifying these bubbles uses a machine learning approach called a random forest approach. All right, so here's how you might classify a cat. All right, you have an image of something. Does it have a tail? All right, no, that's definitely not a cat. Right, does it have legs? How many legs? Right, in the end, you can identify whether something is a cat by its mass and tails and so forth, or whether it's something completely different. All right, so we can use the same process to identify features in astronomy data, right? So when we apply an algorithm like this to that Spitzer Space Telescope survey, we end up with a lot of images that look like this, which are yellow bubbles. Now, these are probably driven by much lower mass stars, maybe a few solar masses. And it's significant because these are much fainter, smaller features, and they are probably missed by citizen scientists. So by combining the simulations and these synthetic observations and machine learning, we can improve our detection of features. So this is great. Now, not all astronomy data is two-dimensional. And in fact, a lot of it has 3 dimensions. So this is an observational data set of a nearby molecular cloud, and it's showing you position in the plane of the sky, and the 3rd dimension is velocity. So it's showing you how that gas is moving along the line of sight. Now, if you guys stare at this long enough, I'm sure you can start picking out features of bubbles. But it's not quite so trivial as that other data set, all right? So for reference, here are 2 of the bubbles, all right? So in order to identify something like this in the complex data set, we need a much more sophisticated machine learning approach. So the one that we're using is based on the human visual cortex, convolutional neural networks. All right, so like the other approach, it's a supervised learning approach, which means it requires a training set to learn what it is supposed to identify. So let's suppose that we have an object. Let's call it a cat, right? Yeah, I love cats. This is my cat. Yeah, he's a great model. So if I ask you guys, and I expect an answer to this, why is that a cat? What makes a cat like? It makes noises, but that's not part of our data set. What else? All right, it looks like a cat. Okay. It's disinterested. Yet those are psychological aspects of cats, which are also not part of the data set. All right. It's fuzzy. There we go. All right, it has paws. Exactly. Okay, you're catching on. All right. So it has cat-like features, tail, nose, eyes, ears, right? And so when your brain looks at this, it can identify it's a cat, whereas if it looks at something like this, even though it has a tail and an eye, you realize very quickly that it's not a cat, right? But if you look at something like this, completely different color, different shape, you can't even see the tail, and your brain immediately identifies that this is a cat, right? It's still fuzzy, right? So why is your brain so good at identifying cats? Besides that you love them. Yeah, so the reason is that since you were a small child, you've been collecting examples of cats, right? And depending upon your experience as a small child, you may have positive or negative associations with those cats. But in any case, any child up to the age of 3 will even be able to identify whether something's a cat or not, right? Now, what is stored in your brain is not actually images like these, but something that is broken up into small patterns. So not characteristics, but your brain breaks down the images into its constituent parts to figure out what is inherently cat-like. So if you could go into your brain, a cat might be stored something like this. Yeah. So we can take this approach and use it to understand the constituents of what makes a bubble in astronomy data set. Okay? So here is a simulated image, again showing bubbles. Here's the input and here's the target. So the first step is to train our algorithm. So it tries to figure out what is special about these shapes, then pick the best model, the best set of filters that best represent the image, and then finally we validate it against some new data to make sure it's actually appropriately identifying things. So here it is in action. We start with these 2 images. We run it through our trained algorithm, and we identify this. So not too bad. It's actually 90% accurate on a pixel by pixel basis. We could try and trick it. We could give it something that has no bubbles at all, and it identifies this. All right, so pretty good, pretty good. So right now, we're in the process of training this algorithm with the simulations and applying it to the data. So at that point, we can then unleash it in a Terminator-like style to actually extract features from the astronomy data. So to summarize, the process of forming a star is messy, right? And so, in other words, despite this messiness, amid the turmoil and turmoil of battle, there may be seeming disorder and yet no real disorder at all, right? So by combining machine learning and simulations and citizen scientists, we can identify these significant features in the data, and it allows us to understand the role of feedback and the life cycle of stars within the larger galaxy. Thank you.
Thank you, Star Troopers. So we have some time for some questions. Oh, up top. I can't see. Oh, there you are. I see you now.
Yeah, so this is purely image data. There are people in astronomy that use this to classify spectra. So instead of a 2D image, maybe you have a 1D spectra. This works on all different kinds of data.
Yes, right there.
Hi. I'm not an astronomy person, so here's my real question. What makes you trust this supercomputer?
Yeah, so why should we trust a supercomputer? Yeah, so there's two parts to this question, and break your question into two. So first, there's the simulations. Why do you trust simulations? Why do you trust the output of the computers at all? Right, so one thing we do, we check the physics of the calculation to make sure it understands Newton's laws and universal law of gravitation and all of that. But we also compare it to real data. And so we can check it just by comparing it repeatedly to what we see. And if it doesn't match, then we have to go back to the simulation and then improve it. For the real data. Could be anything. Could be dust emission, could be molecules, whatever we have handy. Yeah, so it could be anything. Could be shapes of bubbles that we're looking at. Could be distributions of stars. There's all kinds of things to compare. For this, so for this particular case, we trained the algorithm on the simulations and then we ran it on the data and it performed well. So that tells us that it's working pretty well if we can use the simulations to train it. Yeah. How does one get one? The answer is a lot of money. Yeah.
Sir, just behind, and then you're next. Yeah.
So how can you trust the citizen scientists?
Yeah. Yeah. So how and whether do you trust the citizen scientists? Well, there's two ways to check that. One is they check some of the results against experts. And it also turns out that not all citizens are equal in this case. There are actually super citizens. There are some people that are really gung-ho. They get in there, identify a lot of images, and they're basically exactly like an expert. So they introduce a weighting, and they upweight those people that do it a lot and are good at it, and they downweight people who are dabblers who may also be messing things up. Yeah.
And so right in front.
Results are driven by computer versus human interpretation?
That's a great question. So how much is
Yeah.
the result? Yeah, how much is the result driven by human interpretation versus the actual algorithm? Yeah, in the training set. Yeah, so I think it depends what goes into the training set. So for example, if we're training on these bubbles and we want to include some of the observational data in the data set, then we have a bias because a human has already gone in there and picked out things that are bubbles. So there's definitely bias. And even with the convolutional neural network where we have simulations that we can use very nicely, humans are the ultimate arbiter. So on some level, it goes back to people. You can't escape it. Yeah.
So one last question right here. Oh, wait. Oh no. What? Sorry, two questions then. Here, go in the back right there. Yeah. You. Yes.
So depending upon the size of the training set, it could take a few hours, could take a few days. So it's a relatively short time scale as these things go. Yeah.
And then that question right there. Yes.
It seems to me you run into an efficiency issue, like if you have to double check the citizen scientist and the computer versus just taking the observation yourself. Is there any way to like get blacklisted or something as a citizen scientist?
Yeah, so he's saying that there's still some checking that needs to be done, and that takes a lot of time, and how do you get around that? Yeah, I think that what you would like to hear is that an astronomer has gone and double checked all the data, but that defeats the whole point of using the citizen scientists, and that's actually not feasible because many of these data sets are huge, right? So there are just not enough astronomers to go over there and just make sure the citizen scientists are doing the correct thing. So it still comes back to looking at things statistically, seeing how well people do in a subset of images, seeing how well the machine learning algorithms do in a subset of images, and test it against those cases where we're pretty confident.
Okay, great. So let's thank Star Trooper again.